Predicting solar irradiance in the ultra-short term is one of the hardest problems in renewable energy integration. When clouds move across a photovoltaic array, irradiance can drop or spike in minutes. Grid operators need to know exactly how much power is coming in, minutes ahead, to maintain stability and execute proper dispatch. But traditional forecasting models hit a wall. Pure time series approaches only look at historical irradiance and weather data, completely missing the spatial dynamics of cloud movement. On the flip side, standard convolutional neural networks struggle to capture the multi-scale, directional nature of cloud formations, and they tend to lose global low-frequency information as the network deepens. Even worse, most models use fixed compensation strategies that don't adapt to different prediction horizons. A short-term forecast needs to track rapid, localized cloud edges, while a longer forecast needs to understand the overall movement of a cloud system. A one-size-fits-all approach just doesn't cut it. To solve this, researchers developed a new multimodal framework called IST. It fuses ground-based sky imagery with meteorological time series data, but the real innovation lies in how it processes them. The architecture is built around three tightly integrated modules: a multi-scale spatial extractor, a step-adaptive frequency compensator, and a temporal attention network. Let's break down exactly how each piece works. First, the spatial feature extraction uses a modified InceptionNeXt backbone. Standard convolutions use a single kernel size, which forces the model to choose between capturing fine local textures or broad structural patterns. Clouds do both simultaneously. InceptionNeXt sidesteps this by splitting the input feature maps into parallel branches, each using a different depthwise separable convolution. One branch uses a square kernel to capture local edges and small cloud textures. Two other branches use elongated horizontal and vertical kernels to detect directional extensions and band-shaped cloud systems. A fourth branch is an identity mapping that preserves the original input without transformation. These outputs are concatenated and refined through a multi-layer perceptron. The result is a highly efficient, multi-directional feature representation that adapts to complex cloud morphologies without exploding computational cost. But extracting spatial features isn't enough. As features pass through deeper convolutions, hierarchical pooling and downsampling inevitably degrade global low-frequency information. This is critical for long-step forecasting, where you need to track the overall evolutionary trend of a cloud system, not just its shifting edges. The model addresses this with a step-adaptive low-frequency compensation unit, or SALFCU. Instead of relying on static skip connections, SALFCU introduces a dedicated memory pathway. It uses a discrete wavelet transform to decompose the fused features into low-frequency structural components and high-frequency detail coefficients. The low-frequency stream is fed through a series of gates. An input gate carries forward the previous memory state. A supplement gate extracts new low-frequency cues from the current sky image. And a forget gate uses the wavelet decomposition to explicitly suppress high-frequency noise while retaining the global trend. The compensated output is then dynamically weighted. Here's the clever part: the weighting coefficient isn't fixed. It's generated by a learnable embedding layer that takes the prediction horizon as input, followed by a fully connected mapping and a sigmoid activation. For short prediction steps, the model automatically emphasizes high-frequency local details to track rapid shading changes. For longer steps, it amplifies the low-frequency global trends. This step-aware adaptive gating allows the same network to flexibly optimize its feature representation across different forecasting windows. Once the cloud features are spatially and frequency optimized, they're fused with meteorological time series data and passed into the final module, TempAttnLSTM. Standard LSTMs are great at capturing sequential dependencies, but they struggle with long-range periodicity and cross-step correlations, especially when dealing with noisy, non-stationary irradiance data. TempAttnLSTM augments the recurrent architecture with multi-head temporal attention and learnable periodic query vectors. Instead of deriving queries directly from the raw sequence, which makes the model sensitive to transient outliers, the attention mechanism uses a predefined periodic query matrix. This matrix injects temporal priors directly into the attention computation, allowing the model to recognize recurring patterns and long-term dependencies. The multi-head attention output is fused with the original sequence via residual connections and fed into the LSTM. Guided by future-time query vectors, the LSTM generates step-aware temporal representations and produces the final multi-step irradiance forecast. The researchers validated this architecture on two datasets: the public NREL benchmark and high-resolution field data from an operational photovoltaic station in Shandong. They compared IST against 9 state-of-the-art baselines, spanning pure time series models, image-only approaches, and existing multimodal fusion networks. The results were consistent. IST achieved the lowest mean absolute error and root mean squared error across all prediction horizons, with a coefficient of determination that significantly outperformed the competition. More importantly, the error distribution was tightly concentrated around 0, meaning the model rarely produced extreme outliers. Ablation studies confirmed every component's necessity. Removing the cloud imagery degraded performance, but removing the time series data caused the largest drop, proving that both modalities are essential. Replacing InceptionNeXt with a standard CNN reduced accuracy by capturing less directional cloud structure. Removing SALFCU broke the step-adaptive frequency balance, hurting long-step forecasts. And swapping TempAttnLSTM for a conventional LSTM weakened the model's ability to track long-range temporal dependencies. What makes this work stand out isn't just the performance numbers. It's the architectural philosophy. By explicitly decoupling spatial multi-scale extraction, frequency domain compensation, and step-aware temporal modeling, the framework directly addresses the physical and mathematical limitations of previous approaches. It treats cloud forecasting not as a black box sequence prediction problem, but as a structured spatio-temporal frequency optimization task. For grid operators, this means more reliable dispatch decisions and better integration of solar power. For the AI community, it's a clear demonstration of how targeted architectural inductive biases, like adaptive frequency gating and periodic attention queries, can outperform generic, monolithic models on highly specialized physical forecasting tasks. If you're working on renewable energy forecasting, spatio-temporal modeling, or adaptive neural architectures, this framework is definitely worth studying. I'll leave links to the full paper and dataset breakdowns in the description. Thanks for watching, and I'll see you in the next one.